Hello, welcome to part 2 of the video series on the differentiation rules. So in this particular video, we will cover exponential and logarithm differentiation rules and go over some examples. So our first differentiation rule here is going to be taking the derivative of the function e to the x. And so as you see, the derivative of e to the x is just itself, e to the x. And this is because this is the only exponential function that is able to track its own rate of change. Okay. In general, when we take the derivative of an exponential function, we know that for exponential functions, whenever we want to track the rate of change of it, or in other words, take its derivative, it is always proportional to the actual function itself. Okay. And so for our logarithm function, not the same, but very similar here. The derivative of that is just 1 divided by x times natural log of a, where a is the base of your original logarithm. And of course, here we have natural log of x. Whenever our base a is e, we end up with this just simplified form of 1 over x. And if you look down here, we have natural log of absolute value of x, and that is 1 over x as well. The difference in between these two is as follows. For here, we're saying that we're looking at the derivative of the original function, which was natural log of x. And we note that the domain of natural log of x is just all positive real numbers. So therefore, its derivative, tracking its rate of change, has to be true for all positive real numbers as well. In this case, whenever we use natural log of x as the variable for natural log. So here, what we're saying is we can plug in any value for x except for 0. Of course, because still natural log of 0 is not in the domain of either natural log of x or natural log of absolute value of x. It doesn't work. So for here, our only restriction is that x cannot be equal to 0. Okay? So with knowing these rules, we're going to go ahead and do these 4 examples here. And so our first one is we want to take the derivative of the function y equals x raised to the 12th, or the exponential x raised to the 12th. So here we see that it fits this profile. So to take the derivative of it, we could write it in Leibniz notation form or y prime notation. This would just be 12 raised to the x, just like how we have here, times natural log of 12. And of course, this is your constant of proportionality there. And so that is pretty much it for that one. For our next one here, notice that we have a constant times natural log of something raised to an exponent. So if you remember your logarithm properties, you'll remember that whenever we have log of something raised to an exponent, we can pull out the exponent and multiply it times the rest of the function. So g of x could be rewritten this way. And so now, once we rewrite it like that, then when we take the derivative of it, we just pull out the constant. And so the derivative of natural log of x is just 1 over x. And of course here we are noting that x would have to be greater than 0, being that it has to be a positive real number. For part C here, we see that we have 4 different terms for its function. We have a power function in one term, exponential, logarithm, and a constant. So if we start off with the power function, remember from the last video that we would just pull down the 2, and then this would be this will be 6 because this has to come down, and then t raised to the 6 minus 1, which would be 5. And then we pull down the negative 3 because that's the constant. The derivative of e to the t, just like it says here, is e to the t. And of course, natural log of t, the derivative of that is just like natural log of x, which would just be 1 over x. So 1 over t here, and then the derivative of any constant is 0. And of course, we clean everything up. And that is what our derivative of the function f of t would be. For our last example, here we see we have b raised to the x, which is e to the x divided by 2, then plus log of something divided by something plus log of something times something. And so the reason I'm saying it like that is because here, if you recall your logarithm properties again, we know that we can rewrite this particular term and expand it out as the difference of logarithms. And here we can expand this out and write it as the sum of logarithms. So if we use those properties, b of x could be rewritten this way. Okay, and so we'll write that out. So for here, if we combine like terms, you'll see that we have log base 2, log base 2. So that would give us 2 of these. And then of course, here we have minus log base 2 of 8, and this is log base 2 of 16. Here, 8 is the same as 2 raised to the 3rd power. So if you recall your logarithm properties, log base 2 of 2 raised to the 3, all that is just 3. And 16 is 2 raised to the 4th power. So log base 2 of 2 raised to the 4 is just 4. And of course, minus 3 plus 4 is just plus 1. And so now from this form, we can go ahead and actually take the derivative of b of x. So here we know our constant is 1/2, and the derivative of e to the x is just e to the x. Plus, we have our constant 2. The derivative of log base 2 of x will just be 1 over x times natural log of 2. And then, of course, the derivative of any constant is just 0. We clean everything up now. And the derivative of b of x is just 1/2 e to the x plus 2 divided by x times natural log of 2. And so this concludes the second video in the series of differentiation rules.